Okay, the graph shows the force against extension for a wire. Calculate the stiffness constant of the wire. So using Hooke's law, we know that force equals the spring constant or stiffness constant times the extension. Okay, so rearrange this, we can get the stiffness constant like this. So force divided by extension, that's actually the gradient, because on the y-axis we have force, on the x-axis we have the extension. So we can get the stiffness constant like this. So it's very easy for this one because it goes through the origin. So just changing y, 14 minus 0 newtons, divided by changing x and turning the millimeters into meters by times it by 10 to the minus 3. You get the stiffness constant like this. Okay, sketch a line for a wire which has twice the stiffness constant of the wire shown on the graph. Okay, so if it's got twice the stiffness constant for the same force, let's say 14 newtons, we'll get half the extension. Okay, so the gradient should be double the stiffness. Okay, so it should be twice as steep. Or another way to think about it is, if we're going to get the same extension, let's say 20 millimeters, we'll have to apply twice the force. So for the red graph here, we had to apply 4 newtons, but for the new spring with this different one, we'll have to apply 8 newtons. Okay, sometimes you might be given an extension against force graph, in which case the change in y with change in x is actually the inverse of the stiffness constant. Okay, in this question we're asked to calculate the work done, i.e. the energy stored to stretch the wire to 70 millimeters. Okay, so work done is force times distance moved parallel to the force. In this case, we're applying a force to stretch something. So if we do force times extension, it's actually the area under this graph here, y times change in x. So we can get the area under the graph, total area under the graph, to calculate the energy stored or the work done to stretch it. So in this case, it's a triangle. Okay, so it won't always be a triangle, but in this case, we can just do half times the maximum force there, 14, times the total extension, and that gives us 0.49 joules. Okay, so what about if we're trying to calculate the work done to stretch something, but it's not a straight line like this here? So we'll have to work out the area in the graph again, but in this case, we'll have to use trapeziums and triangles or count squares. So I'm going to use a trapezium here. So I'm going to break it up into triangles and trapezium like this. And the more trapeziums you use, the more accurate your answer will be. Okay, so first one is a triangle, so 6 newtons times 30 millimeters divided by 2. Okay, that's 0.09, and then repeat again 6 plus 9 there times the height there, so it's 20 times 10 to the minus 3, and then divide by 2, and then repeat that and keep adding it on. Okay, so this one here is not going to be completely accurate because I only took 3 sections there, but if I took more, I would more likely that my answer would be accurate.